Good evening, and welcome to the live sessions for the course on Fundamentals of Additive Manufacturing Technologies. It is 6 p.m., but no participants have joined yet, so we will wait for a few more minutes before we get started. Thank you. Good evening, and welcome to week 5 of the live sessions for the NPTEL course on Fundamentals of Additive Manufacturing Technologies. Uh, this course is taught by Professor Sajan Kapil, who is a member of the faculty in the Department of Mechanical Engineering at IIT Guwahati, and I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. Last week we started looking at uh, additive processes which utilize a liquid material as the feedstock. And in particular, we looked at the stereolithography or the SLA process, which was the first 3D printing process to be commercialized. This week, we'll try to run through all of the other additive processes which use liquid material as the feedstock, and that will involve processes such as looking at other aspects of the SLA process, and then object polyjet, solid ground curing, perfectory, and a few others. So this week we'll be looking at a few of the other subsystems for the SLA process. The first one being the galvanometer or the scanning subsystem, and second one being the recoating subsystem. So as we will recollect, uh, 3D systems SLA, the first 3D printing technology to commercialize, used a galvanometer as the scanning system, a laser beam as the shape of UV light, liquid bite as a shape of liquid, built in the Z direction, and used deep dipping recoating system. While the improved Zephyr version of 3D systems SLA differed only in the usage of top feeding mechanism rather than deep dipping. And we already looked at the schematic of the process. And let us talk a bit about galvanometer. So as I said, a galvanometer consists of a pair of mirrors mounted on motors, and we discussed in some depth about how, because of the very small inertia of these galvanometer mirrors, they are able to rotate very quickly and deflect the laser light over the scanning area at great speeds. Now, the schematics of how a laser beam is deflected in, say, only the X, only the Y, or in a combination of XY motion in the printing plane was already demonstrated by Professor Kapil, and some relevant derivations were also shown in the lecture. So I'm not covering all of them again. What we should be talking about, however, is the advantages and disadvantages of using galvanometer as the scanning system. The advantage, of course, primary one being the very low inertia of the tiny meters, which can move the laser beam at very fast speeds. A typical order is mentioned here, which is of 10 meter per second on the surface of the watt photopolymer. And second is the long life of the galvanometer, which is because of the low inertia. And even though it consists of moving parts, it's basically mounted on a motor. Still, because of the low inertia, it is able to sustain very long lives. The disadvantage, however, is that not all of the laser energy, which is incident on these galvanometer mirrors, gets passed on to the feedstock to be printed. Rather, some of it is lost. And then there is the issue of defocus of the laser beam on the platform and distortion of the laser beam spot shape, which we'll be talking about in a little greater detail. Now, the loss of energy on the mirrors is because some of the energy will be reflected as desired, some of it will be absorbed, and some of it might even get transmitted. Now, this can be overcome by a couple of strategies. I'll just list, say, one or two of them here. So, one is something we can use uh, reflective coating to improve the ratio or the percentage of light that gets reflected in the desired manner. Or second, what we can do is the mirror can be polished. And this can be done by mechanical, chemical, or any other means. as suitable for the mirror material. And these two strategies can just, these can act as some preventive maintenance, or they can help in regaining the performance of the galvanometer mirrors. But something which cannot be solved by any external intervention is the defocusing of the laser beam and the distortion in shape. What is defocusing? Uh, uh, Whenever there is a beam of converging and diverging light, such as the laser beam shown here, we know that it will achieve its minimum spot size or minimum beam diameter at some region. If it is a purely converging set of rays, it will converge to a point. But in the case of laser, we know that rather than converging to a point, it will converge to this minimum section, which is called the waist. And the distance from some reference to this waist is taken as the focal distance. Now, when this ray of light is, say, projected, or when it is scanned in 3D space, and we trace the loci of the waist points or the focal points, it will form a sphere in 3 dimensions. It's also stated here that the locus of the focus point for deflected beam at different angles in 3D space will be a sphere. And so, uh, for the typical 3D printing cases where our build plate is usually flat, while we tune the working distance so that the focal point or the waist is at a desired distance, say it might be on the substrate itself or at some designated height from the substrate, depending on your process optimization. But once we move away from the optical axis, the focus no longer falls on the plate, and there's this significant height difference. And this is what has been referred to as defocus of the laser beam. Now, a few strategies to correct it is with the use of corrective lenses. One of them being spherical lens, whereby we can uh, locate the focal point. Then there is the flat field lens, where you have this incident ray of laser beams. They are reflected at some angle theta, and then using this flat field lens, they can then be focused onto the target plane at some focal distance f. The distance of the focal point from this optical line is given as h, and a relationship has been derived between the distance h, the focal length f, and the angle of reflection, or angle of deflection theta, which is given by h equals f into tan theta. But what we are more interested in is how to move the mirror so that this laser spot can be deflected all over the printing area. And that can be done by controlling the angular velocity of deflection. And thus, a relationship can further be derived, which links the velocity of the focal point on the printing plane with the angle of deflection as well as the angular velocity of the deflecting mirrors. And that is given here as Vh, which is the velocity of the focal point, equals the focal distance f times omega h, which is the angular velocity of the galvanometer, by cos square of theta, where theta is the uh, angle of incidence of the ray of laser beams. And thus, it may be noted that the velocity of the laser beam on the flat surface is a function of the angular velocity, omega h, of the galvanometer mirrors, and the incident angle theta. Thus, if we want to ensure that the ray of or the laser spot moves at a constant velocity, constant speed on the printing plane, uh, we have to ensure that we control the angle of incidence as well as the angular velocity very precisely. The reason we would want such a thing is because previously we have discussed how to ensure isotropic properties for the printed material. The energy density should be the same, and the energy density is of course influenced by the scanning velocity. And so to maintain isotropic properties, we need to maintain constant energy density. To maintain constant energy density, we need to maintain, uh, in most cases, uh, constant scanning velocity. If not constant, at least it has to be proportional to other factors which control the energy density. However, what remains is that the scanning velocity must be very precisely controlled. Here we see that to control the scanning velocity, we need to control two parameters. One of them being the angle of incidence of the laser beams, and the second one being the angular velocity of the galvanometer mirrors. A numerical has also been worked out, and we'll be doing some of our own during the practice time. A second type of lens which can be used is called the F theta lens. And here, the relationship between h, which is the distance of the focal spot from the optical axis, the focal length f, and the angle of incidence theta is given as h equals f theta. And that is why it is called an f theta lens. It was developed to overcome the issues associated with flat fields lens correction. And here we find that the velocity of the moving laser spot VH is simply the focal distance times the uh, angular velocity of the galvanometer mirrors. This is far more convenient because now for most applications the focal distance f will be fixed, so we can directly relate the scanning velocity of the laser spot on the printing plane to the angular velocity of the galvanometer mirrors. Previously, it was also there was also this factor of the angle of incidence theta, which will change dynamically as the galvanometer mirror is being rotated. But now that factor is no longer present, and we can control the scanning velocity of the laser spot directly just by modulating or actuating the angular velocity of the galvanometer mirror. And this slide gives a very good comparison of the three cases: the spherical lens, which is the which was the default case for which we found that the locus of the points in focal points in 3D space was a sphere. Then there's the flat field scanning lens, where the distance h of the focal spot from the optical axis is f times tan theta, and then there's the f theta lens where this distance h is simply f into theta. A second aspect which was discussed as a potential disadvantage of using galvanometers as a scanning system for SLA processes is distortion of the beam shape. And we also discussed this previously, where when a beam of laser is being incident very close to the parallel to the optical axis or at just small angles to the optical axis, we can expect the cross section of the incident beam to still retain its original shape, which in most cases would be circular, unless specifically shaped or designed otherwise. However, when these angle of deflections are large and we are trying to deflect our laser beam at some significant angle from the optical axis, the cross section of the incident beam may no longer be expected to be circular in nature. In fact, it will be elliptical, as depicted in this schematic to the right here, where we are deflecting our laser beam at some angle theta. The beam by itself still retains its cross section, circular cross section, but when it is incident or projected on the substrate, which is flat, uh, the section cut off of the section of the laser beam cut off by the plane, in this case being the build plate, will be an ellipse. The lateral dimension will then become d sec theta, while the other dimension remains d. And the overall effect of this would be a change in area of the laser beam spot. And while the incident energy or the incident power continues to remain the same, now it is just distributed differently in space. And because this different distribution, the energy incident, uh, the uh, the energy intensity at a point will change. If the laser beam reflected through galvanometer by an angle of theta strikes the wet photopolymer bed, the shape of the cross section of the beam will change to ellipse from its original circular appearance. The major axis of this ellipse will have dimensions of d by cos theta, and the minor axis will continue to be d. And the area will then change as a theta equals a naught by cos theta. Here, theta is the angle of deflection, and a naught is the original area of the circular cross section. A second consideration is the change in absorptivity of the surface because of the change in its angle of incidence. So not only is the energy intensity changing because of the change in shape of the incident beam, the absorptivity of the surface or the material is also changing. That is controlled by Beer-Lambert's cosine law, where we see that the energy absorbed by a surface is proportional to the cosine of the angle between the striking beam and the normal. EA equals E naught cos theta, where E naught is the maximum energy corresponding to a case where the angle of incidence uh, was zero, or the beam was normal to the plane, and theta being the angle of incidence. A second class of lens is the telecentric f theta lens, which facilitate normal incidence of the laser beam onto the target plane. The reason for normal incidence being that now we want, not only do we want to ensure that the focal distance is fixed, well, the focal distance would have been fixed anyway. Not only do we want to ensure that the laser spot is always scanning the surface of the printing plane, we also want to ensure that the beam is always falling normally to ensure that the cross section of the beam is no longer distorted, and it is always maintained in its original shape. And second, to ensure maximum absorptivity into the material, which is controlled by the Beer-Lambert cosine law. To affect these desirable characteristics, the telecentric f theta lenses were developed, where you ensure that rather than the locus of focal points being a 3D sphere, they are always incident on the printing plane. And second, you also ensure that this incidence is always normal to the surface. However, there is a major disadvantage of telecentric lenses which has prevented its wide commercial applicability, and that is the scannable area is limited by the size of the lens. Because here, since your rays are always normal both to the surface and to your lens, what we can see is that it is limited by the size of the lens. I cannot scan any area which lies beyond the dimension of the lens itself, because my incident ray must always be normal. And so, if you want to scan a large enough area, you must have a very large lens. And having precise optics is a very costly affair, not to mention that they will be difficult to maintain, and a lot of care must be exercised in the usage. And so we do tolerate a small distortion in beam shape because of a deflection, but we use f theta lenses for their wider applicability and their ability to scan over considerably larger areas considered compared to a telecentric f theta lens. Irrespective, the size of all additive manufacturing systems using galvanometers are limited in size because of these reasons. A typical number would be, say, 250 into 250 micrometer squares. A second strategy which can be used for beam correction is by increasing the height of the scanning system. And the reasoning for it is as follows. So here we have the focal distance, or more precisely the radius of curvature. Let it be r. Now if r is sufficiently large, what we know is that this locus will keep on flattening out with increase in r, and for very high r's in a local region it will be almost flat. So if you have a very tall column in your scanning chamber and a very large radius of curvature, what you will see is that the uh, beam almost is incident, the focal spot is always almost incident on the build plate itself for significant distances. And so if we were to use very tall scanning chambers, or we were to increase the height of the scanning chamber, we can still affect these changes. That is, we can have the laser spot always on the printing plane without any additional optics. And here we have a schematic representation where you have a pair of galvanometers and it is passed through some f theta or eccentric f theta lenses. And here you are also splitting the beam so that you have multiple spots falling on the surface. The second system that subsystem which we'll be talking about is the recoating subsystem. And we already spoke about it a little. We know that in 3D systems SLA, recoating is affected through deep dipping, where the entire built part uh, goes into a vat of resin. Resin is allowed to flow over it. Because of the viscous nature of the resin, this flow takes some time. It is not immediate. Then a lot of excess resin is allowed to accumulate over the built part, and something called a doctor's blade or a roller blade, as the case may be, then wipes away the excess resin. We have some mechanism to check the level or the height of resin column, and then further printing continues. Recoating in a 3D printing process is the process of establishing a new layer of fresh resin over the previously cured layers. A successful recoating step is one that is capable of establishing a fresh layer of liquid resin of desired thickness within a reasonably short time. An incorrect layer thickness will adversely affect the accuracy of the product, and owing to effects related to the viscosity and substitution properties of the liquid resin, it is not easy to make this design. And there's a typical recoating cycle will have many complex steps such as leveling, deep dipping, elevating, sweeping, obtaining the new build position, and then set weight. And let us just talk briefly about all of them one by one. The leveling step in the recoating process is described here. So we know that because of the polymerization process and subsequent curing, the resin will undergo some shrinkage. Typically, it undergoes about 5 to 7% volumetric shrinkage. If the resin did not shrink upon polymerization, this leveling step would only be necessary at the start when you expect some liquid currents in the resin at the start of printing in a new layer, and to ensure that the resin in this case was at the proper or desired Z height. A level compensation system, which may either be some contact type in which you have a probe which scans over the new layer, or non-contact type such as optical or some reflect light type, is implemented in SLA. The level compensation system maintains tolerances in the Z level, and as we discussed, any variations or deviations in this layer height for each layer can lead to several deficiencies in the final built part, such as poor surface finish, loss of accuracy, and so on. And if the resin lies within the desired tolerance limit, the levering operation is said to be completed and the process is allowed to move on to the next step. Let us talk about deep dipping. The elevator, which is just the build stage, fully immerses the previously completed part under computer control to allow the resin to flow and accumulate over the part. Owing to the high viscosity of the resin will take quite some time before it assumes a level surface over the part. This leads to the formation of a depression in the resin surface above the part, especially in regions where there may be any cavities. And the depression can be quite significant over regions with trapped resin volumes, as I just said. Such volumes occur when there are pockets of liquid resin within the part interior that do not have connecting passage to the rest of the liquid in the vat. The time Td taken for the depression to be thus closed has been studied by various means of viscous flow analysis and experimental studies, and some proportionality relationship has been found and described here, which is Td, time taken for depression to be closed, is proportional to Rc, mu, and inversely proportional to Hd square, where Rc is the critical circle radius for the given cross section, mu is the dynamic viscosity, and Hd is the depth of the depression. Now, what is the critical circle radius for the cross section? We know that these cross sections are obtained when the 3D CAD model or its suitable approximation by an STL file is sliced using the slicing layers or the non-conformal slicing surfaces, and the contours are generated. These contours contain the cross section in a particular layer. Now, for that cross section, the critical circle defines the maximum distance on that cross sectional geometry that the resin must travel to flow off the part. So assume that there is a lot of resin accumulated on top of this cross section, and if you just let it be at t equal to 0, it will try to flow off of the cross section. So the maximum distance which it must travel starting from a given point is called the radius of the critical circle taken at that point for the given cross section. A few examples are shown here. Say for this square section, R1 is the critical radius, which is equal to exactly half of the edge length. This is not the this is not the longest distance from the center of the given circle, as say for instance half of the diagonal length will be longer than this radius. However, it is the maximum distance that the resin will travel before it can fall off. Similar examples are given for this triangular cross section and the arbitrary cross section on the right. Since for a given resin material, the value of mu will be fixed, and once your CAD geometry has been finalized, the value of the critical radius in its cross section for each layer will also be fixed. Thus, the only possibility for reducing time taken for filling the depression is by increasing the dipping height, as we saw that Td is inversely proportional to square of Hd. Any changes in Hd will have a far more drastic impact on Td than Rc or mu. That is why we rely on deep dipping and not just say sufficient dipping or little dipping. If we can make it deep enough, then the depression will fill much faster. So here we also have an example numerical where we are asked to find the ratio of the deep dipping time required for the two cross sections shown in the figure. So say this is my cross section 1 and this is cross section 2. What is the critical radius in each case? For the first case, let us try to sketch the critical circle. The critical circle will in fact overlap with the given circular geometry itself, and thus the critical radius will equal will be equal to the radius of the circular cross section, which is equal to d by 2. What about the other case? It is a donut-like cross section, also called a torus. And notice that here the critical circle is neither this inside circle, which I am currently highlighting in blue, nor is it the outside circle, which I am now highlighting in red. We have to make the critical circle for the cross section. And the cross sectional area here is the area contained between these circles. And so the circles which I am drawing right now are the critical circles for this case. And thus the critical radius will be the radius of the circles in green. This is given to us as half of the diameter of this circle, which will be half of, say, half 3 by 2d, which is radius of the outer circle, minus d by 2, which equals half of 3 by 4d minus 2d by 4, which is d by 4, or d by 8. And so we can find out the ratio of the deep dipping time for the two cross sections. So TD1 by TD2 will equal RC1 by RC2, assuming that other factors such as the viscosity and the depth of the depression are equal. And this then becomes d by 2 by d by 8, or 4 times. Next step, or the next process, is the elevating process. So just a small typographical error here. This is excess material. The third stage, once the depression has closed reasonably, is called the elevating process. And here the platform is elevated till the top layer of the part is above the resin surface. Take note of the schematic here. Here in this first line, which I am drawing in black, is the layer of the resin inside the vat. The second line, which I am now drawing in red, is actually the height of the part which has been already deposited. Notice how it is taller than the height of the liquid resin within the jar. And on top of this, highlighted in green, is say the profile at some time of the resin which has been accumulated on top of this printed part. As a result of this, there will be a layer of thickness exceeding the desired layer thickness TL resting on the part's upper surface. And this step is required so that during the next step of sweeping, only the excess material above the part should be disturbed instead of disturbing all of the remaining resin. Now imagine if the recoating blade or recoating roller here, shown here, were to pass over the entire layer of resin in the vat. It would have introduced surface waves over the entire vat, and the resin would have actually adhered to and stuck to this doctor blade and moved with it because of viscosity. And thus, such perturbations would have taken a very long time to settle. It would have led to loss of productivity. Thus, we elevate the part a little above the resin surface so that these surface waves can be avoided and the roller or doctor's blade will interact only with the elevated part of the resin, which is above the printed part. So at this point, the recoating blade traverses one end of the vat to another end and sweeps the excess material. In terms of numbers, it is said that for majority of part geometries, the optimum sweep period is about 5 seconds. However, the recoating behavior is quite sensitive to the presence of trapped volumes of resins in the part. And we have a small comparison of scales here. For parts without trapped volume, changing the blade velocity in the range of 5 to 120 millimeter per second does not significantly affect the final layer thickness. However, this is not the case when there are trapped resin volumes inside. Now, what we can expect is that had the resin been not so viscous, then the resulting layer thickness L would have been equal to the uh, preset gap for the doctor blade sweeping over the resin layer. However, because of this viscous nature, there is a leading edge bulge at the leading or say advancing edge of the doctor's blade, and there is some adherence of resin to the build blade at the trailing edge as well. And then far away behind the blade, we have the uh, desirable layer thickness TL. And under certain assumptions, a relationship has been derived between the desirable layer thickness and the layer thickness just at the trailing edge of the doctor's blade. Now, owing to finite surface tension effects, some resin has adhered to the trailing edge of the blade, as we just discussed. Due to viscous drag, there will be a bulge close to the leading edge, which will be far more than the desirable layer thickness. A consequence of this is that the actual layer thickness TL following the sweeping process will be smaller than the gap LG. And for a triangular distribution of velocity from the part or substrate to the blade, this relationship has been found to be equal to TL is equal to LG by 2. Thus, the desirable layer thickness is equal to exactly half of the layer thickness at the trailing edge of the blade. Once the doctor's blade has swept over the part and swept away the excess resin, the next process involves obtaining the build position. Here, the elevator is again lowered so that the part is in the right position for scanning the next layer. The resin surface at the beginning of the stage is still disturbed. However, the disturbance, as we discussed, is not because the doctor's blade or recoater interacted with the liquid resin. It is because of the motion of the stage and the deposited part into the vat of liquid resin. In particular, owing to finite surface tension effects, there is usually a visible crease at the solid to liquid interface around the perimeter of the part. And this crease decays exponentially over time. Lastly, there is this period called Z wait. It's a waiting period which is introduced for the resin surface to blend and reach the configuration as shown in the figure. Basically, it is the time allowed for the surface waves or perturbations to die out. The Z wait period is usually determined through a compromise between surface non-uniformity and the build time. That is, if you have the allowance of a large build time and you can spare enough time, we can really wait for a long time for these surface perturbations to settle, which will give us very good surface finish. However, as typically the case will be, if we are constrained on build times, we will have to compromise on the surface non-uniformity, and after a reasonably good amount of time, where we expect, say, most of the surface perturbations to die out, or at least the amplitudes to be, say, significantly small, we can then continue on with the building process. One needs to choose longer Z wait times when a large layer thickness is chosen. However, with current technology, it is possible to complete the computation and adjustment of resin layer per layer within 1 second. However, a practical part built by a process like SLA, which will have layer thicknesses in the order of, say, some tens of microns, will consist of thousands of layers, and thus even a second of wet time will eventually add up to be quite significant. How the improved Zephyr systems uh, are different from the existing or the first perfected SLA systems are in the usage of a vacuum blade which picks up resin from the side of the vat and applies a thin layer of resin as it sweeps across the part. This speeds up the build process by reducing the time required between layers, and it also greatly reduces problems involved when building parts with trapped volumes. The final subsystem, which is related with the z-axis of the SLA system, is the usage of the motion mechanism for this z-axis. And various types of kinematics have been used, including the usage of lead screw or ball screws, the usage of rack and pinion, or the usage of parallel kinematics such as a scissor lift. Each of them have their advantages and specific applications. In particular, scissor lift, which uses parallel kinematics, tends to give you very large build volumes, that is very long heights, with a very small footprint in the XY plane or the print plane. A few other processes which also use liquid feedstock for printing of parts are perfectory and object polyjet. Some of the subsystems of perfectory are DMD or digital mirror device, also sometimes called a digital micro mirror device, the recoating system, and curing. So for object polyjet, we use flying liquid and a floodlight. The liquid is available in the form of a jet. Printing takes place along the positive Z direction, and the mechanism of feeding is top feeding, whereas for object polyjet, sorry, this was for object polyjet. For perfectory, the scanning system is digital light processing using a digital mirror device. The light is available in the form of a floodlight. The liquid is available in the form of a vat. Building occurs along the negative z direction, and since we have the negative z direction build, of course we use bottom feeding. Uh, some details about perfectory. It is photopolymerization based AM system with the best cost to performance ratio, providing better accuracy and greater resolution than SLA with far lower capital and running costs. It is driven by DM technology and was invented in Germany. The distinguishing feature, of course, is in the usage of this digital mirror device, which is actually an array of many tiny mirrors. These mirrors are suitably reflected or actuated using electrostatic coils, which then reflects the incident UV radiation onto the uh, same resin to be printed. Here, as we can see, the print is happening along the negative Z direction, and the photoresin is available in the vat. For the laser or the UV, sorry, not the laser, for the UV light to interact with this layer of resin, the window at the bottom have to be transparent. So the steps in building a part using Perfect Tree are the exposure step, where the new layer of resin is exposed to the incident UV light, peeling, which here is shown as some type of shaking. Okay, sorry. Uh, Let me just try to write with a finer ink. Shaking or some vibratory mode of separation. Then you have the waiting period where you allow some time for a fresh layer of resin to flow under your built part. And then there's a leveling step. In the case of Perfactory, the inverted build platform improves the part quality and speed because of the reduced cycle time, which comes most from the usage of a UV floodlight compared to UV laser. Here we are, say, exposing our entire print area to UV radiation at the same time instantaneously, rather than scanning it point by point using a laser-like source. Second is by minimizing the need for support structures and say when minimizing any potential regions with trapped volumes, as we have been discussing over the past couple of weeks. For prints which utilize a negative build direction, the need for support structures is automatically minimized, as well as if there are any hollow volumes under the action of gravity, the liquid resin will flow out of these volumes on their own. An example which I might have given before is in the case of printing a hollow sphere, where say this is my build plate and I'm printing the hollow sphere. In one case, uh, along the negative z direction, and in the other case along the positive z. When building along positive z, we will have some support structure at the bottom to allow for machining allowance, and then support structures to support these overhangs, and also support structures inside support the overhanging features on the inside. Whereas when building it along the negative z direction, you might still have some supports to allow for machining allowance or to allow it to separate from the build plate. But that is about it. We do not need, say, any additional support structures because now the structure is entirely self-supported. Further, if any resin enters this hollow region, there is a very good chance that it will remain entrapped in building along the positive z direction compared to the negative z build, where any resin which might have entered this hollow region will automatically flow out under the action of gravity. Then there is no usage of laser, which saves us considerable costs in terms of sophisticated optics. And then there is the use of mask projection with DLP, optical semiconductor technology, which have very long lives, say of the order of some 22,000 hours. Here we also have an example which shows the power of the perfect ray technology. On the left hand side, you have a single pillar of material, and on the second, you have a array of pillars. Now imagine you're trying to build them by SLA process. In SLA, the build time will depend on the number of layers, of course, but also on the cross section or the area which has to be printed in each layer. Because in SLA, we are using a laser beam which will scan the desired region point by point. Whereas in the case of perfect tree, we are shining a floodlight on the area to be printed. Because of shining this floodlight, the entire printable area can be cured in a single go. Hence, and the process is almost instantaneous. Hence, the area to be printed per cross section does not really influence the total print time. It is just the number of layers which will affect the printing time. Here, the various subsystems are also highlighted. And as I said, the distribution feature of Perfectory is the use of this digital mirror device or digital light processing technology. A digital micromirror device is a binary light modulator which consists of a rectangular array of square micromirrors that can be tilted around the diagonals. They are called micromirrors because typically the dimensions of these mirrors will be in the micrometer range, and they will have two stable positions, the off state and the on state. When the device is not powered, the micromirrors will lie flat and normal to the surface of each mirror is aligned with the optical axis of the device. The one on the top here is actually the off state. When the DMT is powered on by the usage of electrostatic coils, the micrometers can be individually actuated and deflected and rotated into either one of their two fixed operating positions. Those positions being the mirror tilted 12 degrees from the normal to the surface of the device, sometimes referred to as the on state and the off state. Professor Kapil also displayed an ingenious example of a DLP-like mirror, which was very educational. Uh, we also have some basic terminology related to the digital light processing technology, which are summarized in this slide. We have the micromirror pitch, which is the distance between the centers of two neighboring mirrors. We have the micromirror size, which is the linear dimension of a mirror, and we have via, which is this this small circular region uh, in the approximate center of each mirror. We have a small non-reflective part in the center of each micromirror through which the mirrors are mounted onto the underlying hinge structures. This is the region through which the mirrors are connected to the underlying hinge. The mass of mirrors in DLP is also very low and it does not create any noise. The DMD can work for up to 22,000 hours. Just like in a 2D printing technology, uh, the 2D surface or the the say shape or pattern to be printed is discretized in the form of two-dimensional pixels. Its 3D analog is the voxel, and thus we can find the resolution of a perfectly like system. If we assume the resolution of DMD is some A cross B, which is the minimum feature size which is can print, the total number of pixels will be A into B. If the work area selected is the total work area, which is say some x times y millimeter square, the area which has to be assigned per pixel is actually xy by AB. Typically, you will be working with square pixels or pixels whose aspect ratio will be 1 to prevent any distortion effects. Thus, the square root of the area per pixel will give me the pixel dimension. And given that I know that the cross section of the pixel has aspect ratio 1, I can multiply it by the height of the voxel to obtain the volume of the voxel. And it is also visualized here with the use of a few numbers. We'll be also solving some similar exercises later today. As I mentioned, to allow the resin material to interact with the floodlight of UV, coming from the bottom, the window or the surface at the bottom of this resin tray must be must allow this interaction. It can happen in a couple of ways. First is that uh, the transparent window can allow the infusion of oxygen. So typically, this window material is actually silicon, and this allows the infusion of O2. What this O2 can do is, say, over time, because of the constant sticking and separation of the resin from the silicon window, there can be some remnants left, which will build up with time and eventually will start to affect the total amount of light which is able to pass through this window and interact with the resin. The usage of photo will maintain a small curtain of oxygen, which will keep the resin separated from the silicon window and prevent this buildup. However, we know that oxygen can be tricky to handle and can lead to potential hazards, and so it is best avoided. The second example, which was demonstrated by Professor Kapil, was the use of a flexible transparent window where separation of the build part from the window was sufficiently easy. A third example is that of peeling and sliding, where, say, if we are looking uh, from the top, and if I also draw the front view, so let this be the cross section of a build part. On one side, we have an optimum uh, layer of uh, resin present. Let the right side be the optimum side here, and the other side can be the excess side. What happens is, when printing in a particular layer is completed, this object can then be slid to the other side, where now uh, it gets separated from the transparent window, and uh, resin can flow underneath the printed part for accumulation for the next layer, which is expected to be printed, and then it can be slid back towards the optimum side, which automatically ensures that the amount of resin present corresponds to the desired layer height. And this is very useful because, as we know, we are using liquid feedstocks here, and liquids are, uh, say, weak in shear. And so by shearing, the printed part can be easily separated from any liquid resin which may be present underneath it. The next technology that we'll talk about is object polyjet, which uses both flying liquid and flame optics as the scanning systems, which uses floodlight as the shape of UV light, where the liquid is available in the form of a liquid jet. Build occurs along the positive z direction, and the recoating system is via top feeding. The object polyjet is very similar to SLA in principle, where when a light of appropriate wavelength falls on liquid photopolymer, the energy absorbed by it causes polymerization. The polymerized photopolymer will be in the solid state. Here, the principle of inkjet printing is used, and ink is replaced by liquid photopolymer. Raster-based printing technology is incorporated here. Multiple jets are used to improve productivity. Uh, 8 pairs of jets have been well documented, and this will keep on improving with improvements in MEMS technology. A flood of UV light is shown on the table when printing takes place, and explicit support structures are required where water soluble gel is used as a support which is not photosensitive. At the end of print, this support can simply be blown off by a jet of water. Here we also have a schematic representation where we see that the jetting head contains the X and Y motions. The UV light is also mounted on either side of this jetting head, and thus both the flying liquid and flying optics principles have been used. As we can see, the two types of materials, the build material and support material, have been shown using two colors, yellow and white. The support material is built using a separate material, which is say vulnerable to dissolution in water. Previously, we discussed how if it is not possible to use two materials, we can use a single material with some additional strategy, such as by making them less dense or by partially curing the support and the parts, breaking the supports manually and then fully curing the part. Here, it is possible to use two different materials very precisely using these jetting heads, and the support material can simply be dissolved in water. Here, the names given to the model and support materials are full cure M and full cure S. Now, as we discussed, the object polyjet deposition head has 8 heads, which allow for synchronous jetting with the sophisticated head, simultaneous jetting of the support and build materials, which allows for super thin layers and layer resolution of 16 microns, and the immediate UV curing of each layer by the UV floodlight, which is mounted in the deposition head itself. Further, if any of the heads were to malfunction, it is very easy to replace the jetting head, uh, for which a standard procedure is prescribed. Uh, the determination of which head is malfunctioning is also highly standardized. And just like inkjet printers, the object polyjet is very suitable for usage in office-like environments. Some of its advantages and limitations are mentioned here. So, because of the very good layer resolution of 16 micron, it can print very accurate and detailed models with smooth surface finish and of any complex geometry. It is very fast because it uses a raster-like printing strategy, where X is the axis along which is being printed, where Y is just the indexing. We discussed how for such processes, uh, the head can simply move by a fixed distance along any one axis as an indexing process, thereby making the process super fast. And then there are 8 deposition heads and multiple jets, which also reduces the number of indexing. The printed parts have been documented to show good material properties with good flexibility, high impact strength, and it is also suitable for the printing of transparent materials, thereby making it suitable for applications in photoelasticity. The operation is very easy. Uh, it is the technology is reliable, easy to use, and removal of supports is very easy as we discussed just by dissolution in water. The process is very clean. It does not generate any toxic fumes or any hazardous byproducts, thereby making it suitable for office environment. No post curing of any type is required. The build material is cured entirely in the process itself. Maintenance is also fairly easy, and any set of nozzle can be replaced individually. It has been very well applied to uh, make, say, this shoe sizes or molds for automotive and service bureaus. Limitations of the process are very similar to SLA since it is based on the SLA technology itself. And just like since it is analogous to inkjet printing, the concept of dots per inch or resolution in terms of DPI also carries over, where because of the rectangular source of UV light, the resolution can vary. It also depends on the material flow rate, the speed of the head, the size of the head, and other factors. And what we can see is by packing more number of nozzles into the deposition heads, we can approximate any complex geometry better and better, as shown by the example of changing the dots per inch from 10 to 300 and how it approximates a circle. The final set of slides for this week deal with some other liquid AM processes, those being AutoStrad's EDART, solid ground curing, microstereolithography, robotic SLA, and a few other processes. AutoStrad, which is a Japanese manufacturer of stereolithography systems, uses a system where the X and Y axes are mounted onto the laser source. The laser source always acts normally to the liquid bed, thereby ensuring neither beam distortion or loss of beam focus. Whereas the Z motion is available with the stage. Also, now since the resin or the vat of liquid is not moving, any surface perturbations or surface waves in the liquid are minimized. But the downside is that because of the motion, X and Y motion of the laser source, it is not a very fast process because we cannot move those optics at great speeds. The laser beam is directed into the resin, which is in a container with a clear bottom plate, and the system uses an acrylic resin to produce the models. It uses laser beam, so again the process would be slower compared to any other process which might have used a floodlight. And the platform or modeling base is raised upwards each time a layer is completed. Otherwise, it is very similar to the SLA process already described. Some of the advantages are the benefits which are otherwise associated with any top-down build strategy, and the lack of any requirement for beam correction as we just discussed because the laser beam is always incident normally to the resin. Then there is solid ground curing, which uses a mask as the scanning system, uses floodlight as the UV light. The shape of the liquid is in the form of a vat. Build occurs along the positive Z direction, and the recoding system uses top feeding. It is also very similar to SLA, and when a light of appropriate wavelength falls on the liquid photopolymer, energy will cause polymerization, leading to solidification of the liquid polymer. In the case of solid ground curing, a flood of UV light is used as opposed to a laser light in SLA, and the flood is made to pass through an optical mask. Thus, any disadvantages associated with, say, an optical lithography process, where there is some distortion in the beam shape and beam in the mask shape and mask size, uh, when it interacts with the actual material, will also carry over here. The mask is the negative of the region to be polymerized, and the regions of liquid polymer where the light falls become solid. As the entire area is exposed at a single time, the process is considerably fast, and the build time again is proportional to just the height of the object and not the volume, because here we are just concerned with the number of layers, not the area to be cured per layer. The power of the laser and exposure time decide the layer thickness, and explicit support structures are required, which in this case is achieved by pouring wax in the regions not affected by the light. And a very useful schematic of the process is also shown here, where first, corresponding to each layer that is to be deposited, we have to create the photomask. Second, we coat the build plate or any pre-existing layer with resin. The photomask is placed at an optimum distance from this resin, and then the UV lamp is turned on. The resin is then partially cured. And the uncured liquid is removed. A layer of wax is coated on top of this partially cured resin, and even the excess wax or any uneven wax which may be available on the surface is removed away. One may think that some time is needed for the wax to solidify, but in this case, something like a cold plate can be used to accelerate the freezing of the wax. Once the wax has sufficiently frozen, it is face milled to ensure good tolerance in the Z direction. And once this face milling operation is completed, the final curing using a high power UV lamp is performed. And thus, in these 8 steps, we complete printing of a single layer, and then the process can be further repeated. The advantages of the solid ground curing process are that the entire layer is addressed in one go, hence it's fast. No post-cure treatment is required as polymerization is complete in the machine itself. In the 2 curing steps that we just saw, the milling step of face milling ensures flatness for subsequent layer and good Z accuracy. And this approach is also adopted in a few other systems for very high accuracy. The supports are obtained by filling wax after sucking the liquid polymer which is excess. No additional calculations for support structures are needed. However, the process has 2 cycles and many subsystems, hence it is less reliable, and there are the chances of errors or malfunctions is increased. Furthermore, the process being complex requires a full-time operator attention. Second, build time depends only on the height of the part and not its volume, which is good for large volume parts. But if your part has very small volume, but it has a long aspect ratio, it will still take a long amount of time, even though the total entire build volume will be small. The dewaxing process is pretty time consuming, and it also creates a lot of waste wax. There are a couple of other niche processes, but they are not really well commercialized. And Professor Kapil has described them in good detail. So we'll just take a short break here, and when we return, we'll be solving a few numerical examples which will help us with the assignments for this week. So let us meet in some time. Hello and welcome back. And let us continue with the session. Now we'll look at a few numerical examples which will help, say, improve our understanding of the concepts and will clarify any doubts which might have remained after the revision. And these will definitely help you in solving the exercise problems for the week, as well as if you have registered for the course certification examination, then in answering the questions in that examination as well. The first question is asking us to find the range of angular velocities for maintaining a constant laser velocity on the printable surface. And it says a single axis galvanometer with a range of plus minus 20 degrees Celsius is used in an SLA process. The laser beam deflected from the galvanometer passes through a flat field lens to keep the focal point at a distance of 300 mm on the top of the resin surface. What will the difference between the maximum and minimum angular velocity of the galvanometer in order to keep the constant velocity of the laser beam spot to 10 meter per second? So we already discussed this a little while back, and I will directly use the formula available in the slides, which was that the velocity of the laser spot on the print surface is equal to the focal length times the angular velocity of the galvanometer by cos square theta, where theta is the angle of deflection. Let us try to identify the parameters from this given data. So the parameters given to us are that the range of theta is between plus minus 20 degrees. The focal point is at a distance of 300 mm, thereby meaning that the focal length itself is 300 mm, and the required constant velocity of the laser beam spot on the print surface is 10 meter per second. 10 meters per second. Now we can plug these into the given equation and obtain the range for the angular velocity of the galvanometer mirrors, omega h, and then we obtained as Vh times cos square theta by f. Vh is 10 meter per second. The focal distance is 300 mm or 0.3 meter times cos square theta, which is equal to some 33.33 cos square theta. Now a range of theta is prescribed to us, and we have to decide based on this range of theta the maximum and minimum angular velocities. Notice that the angular velocity is a function of cos square of theta. So it will yield the same result irrespective of whether we use minus 20 degree or plus 20 degree as given to us. Thus, the extreme value alone cannot give us the range for angular velocities. Notice also that omega h will be maximum when cos square theta is maximum, which will happen at theta equal 0. Therefore, omega max is equal to omega h at theta equal to 0, which will simply be 33.33 radians per second. What about minimum? So we know that the value of cos theta decreases as theta increases from 0 to 90 degrees. Thus, the minimum velocity for the given range of theta can be expected at the extreme value, either minus 20 or plus 20 degrees, because we are working with a cos square term. So omega h is minimum when theta is equal to, I am using plus 20 degrees, but the result will be the same even at minus 20 degrees. So omega min equals uh, omega h at theta equals 20 degrees, which equals 33.33 cos square of 20 degrees radians per second. Please allow me a minute to work this out. So this will come out to be 33.33 times 0.8830, which comes out to be 29.43 radians per second. Thus, for the given range of theta, to obtain a constant velocity on the print surface, we have obtained the necessary range for angular velocity, and that is given by maintain the velocity equal to 10 meter per second. The angular velocities must lie between 29.43 radians per second and 33.33 radians per second. The next question is on the laser beam shape distortion and says that a single axis galvanometer with a range of plus minus 25 degrees is used in an SLA process. The beam deflected from the galvanometer passes through an f theta lens to keep the focal point at a distance on top of the resin surface. The area of the circular laser beam spot on the resin surface is 2 mm square. What will be the laser beam spot area if it is deflected through the galvanometer by 20 degrees? So in this case, let the original spot area be A naught. The new spot area after deflection of the beam by an angle theta may be denoted as A theta, and as we saw in the slide, it is equal to A naught by cos of theta. Again, here we are given that from the question, this original area is equal to 2 mm square, while theta is equal to 20 degrees. Therefore, the new area can be simply found as 2 by cos of 20 degrees is equal to 2 by 0.9397 millimeter square, which is equal to 2.1284 millimeter square. The third question is asking us, what is the advantage of using parallel kinematics in the z-axis subsystem of SLA systems? Is it lower cost? Is it a speed advantage over the use of lead screw or ball screws? Is it that relatively larger build volumes can be obtained, or is it the reduced footprint in the build plane? Now, while going over the slide contents, we discussed how by using parallel kinematics, such as the use of a scissor lift, we can have a relatively larger build volume along the z direction while simultaneously maintaining a very small footprint in the xy plane or the printing plane. However, we did not have any conclusive evidence to say that the usage of parallel kinematics will render any speed advantage over the use of lead screws or ball screws, or that it will necessarily result in lower costs. So A and B are the correct options here. Question 4 asks us, in the context of 3D systems SLA process, what should be the gap between the doctor blade and the pre-built layer in order to obtain 10 micrometer thickness of the layer? So let us just quickly revisit the relevant slide to talk about it. And here we saw that because of the viscous nature of the resin, it adheres to the doctor's blade, and there is a leading edge bulge in the leading edge of the blade, and there is some increase in the resin height at the trailing edge of the doctor's blade as well. In the present case, we are asked to find the gap between the doctor blade and the pre-built layer in order to obtain a 10 micrometer thickness of the layer, and we saw that if the layer thickness is denoted by TL, it is equal to Lg by 2, where Lg is the thickness of the resin layer at the trailing edge of the blade. The question requires us to find Lg, which will be equal to twice the desired layer thickness. Since the desired layer thickness in this case is 10 micrometer, therefore the gap between the doctor blade and the pre-built layer should be twice that, which is equal to 20 micrometers. The fifth question is asking us, what factors influence the build time in the SLA process and in the perfectory process? And we see that it is some combination of the height and volume of the build part. We can reason this one out by remembering that SLA used laser process which scans point by point over the region of interest. In a slice. Whereas Perfectory used a floodlight which illuminated the entire print area in a slice in one go. And thus here, in the case of SLA, we were concerned with the area in a slice as well as the number of slices. Whereas in the case of Perfectory, because we are anyway exposing the entire print area, we are no longer concerned with the area in the slice, we are only concerned with the number of such slices. Hence, in a way, it can be seen that for Perfectory, we are concerned with the height of the build part. Whereas in the case of SLA, it's the height, but also the area per slice, the product of which gives us the volume. So in the first case, it is the volume for SLA, and for the second case, it is height for Perfectory, and we see that option B is the suitable option here. In the sixth question, Whereas that in Envision Text per factory, a DMD of resolution 2048 into 1024 is used. If the working area is 300 into 150 mm square, find out the resolution of the machine at maximum work area setting. So you might have encountered a similar problem in your assignments also, and that is this we're going to solve it. I'll be using formula that are available directly in the slides and will not be deriving them again. The total pixels available to us are 2048 into 1024, while the working area available to us is 300 into 150 square. This entire working area has to be shared by the pixels. Given this, the area per pixel denoted as AP in the slides as the working area by the number of pixels which is equal to 300 into 150 by mm square by 2048 into 1024, which is equal to 0.0214 mm square. Now, in the slides, we discussed how typically your pixels will have an aspect ratio of 1 to avoid distortion. And so we can continue with that assumption. That is, we assume square pixels of side AP. AP square equals the area per pixel, which implies AP will equal under root of 0.0214 mm, and this comes out to be 0.1465 mm. This is the required answer for this question. The seventh question asks us, which of the following statements are true with regards to energy sources in liquid AM processes? We have been talking about the liquid AM processes for a couple of weeks now and encountered a variety of energy processes of energy sources. The first statement says that lasers are coherent, monochromatic, and cost effective. Indeed, lasers are coherent, lasers are also monochromatic, but lasers involve a lot of sophisticated optics and thus they are not cost effective. Floodlighting is not coherent, but it can be monochromatic and it is cost effective. Lasers are monochromatic, but floodlights are not coherent. Floodlighting is monochromatic and cost effective. Thus, option D is the only correct option here. What physical principle is utilized for sliding based recoating system in Envision Text per factory? Is it that sliding requires less force due to shearing of liquid resin layers? Is it that sliding ensures uniform recoating of resin for the next layer? Sliding is a simpler mechanism than using a recoater blade? Or that the inertia of sliding ensures liquid resin fills up the voids and pores of the previous layer? We are asked about the physical principle for sliding based recoating systems. Please recall that this recoating system had a step where the part which is already cured in the previous step had to be separated from the transparent window. And this was achieved by a motion uh, of the sliding type. Why was this sliding motion preferable, say, to a vibratory or shaking or tearing away like motion? That is because the liquid resin layers present uh, between the cured part and, say, the window are, as well as surrounding the cured part, are, uh, say, weak to shear, and thus sliding requires very less force. So option A is correct. Question 9 is asking us, what material is used for generating support structures in object polyjet? Remember how we discussed about object polyjet and how it can use two different materials for printing the build regions and the support regions. The question is asking us, what is the material used for generating support structures? Is it same as the build material? Is it a water soluble gel? Are no support structures required, or is wax used? It is not the same as the build material because then it will be difficult to remove. It is not wax because wax was used in a different process. It was used for solid ground curing. Support structures are indeed required based on the type of geometry we use. It is the water soluble gel which acts as the support material in the case of object polyjet. The name of the material in this case was full cure S, which was the support material. The 10th question is asking us, what is the correct statement in the context of UV power uh, of object polyjet versus envisions per factory? Remember that both of these processes use a UV power source. Is the UV power of object polyjet higher than envisions per factory because of the flying optics? Is it lower than envisions per factory because of multiple jetting nozzles? Is it lower than envisions per factory because of lower layer thickness, or is it the same? Now, in object polyjet, we used flying optics where the material was deposited by jetting head, and the UV system, curing system mounted on the deposition head itself, cured this material almost instantaneously by passing over it. Since the time available for this curing method or this curing step was very small, we require a higher UV power. Thus, it is expected to be higher than envisioned as per factory. It cannot be lower because of multiple jetting nozzles because the two are seemingly unrelated. The lower thickness is difficult to comment because the both processes may be using a same layer thickness, and so any distinction based on the lower layer thickness alone cannot be conclusively derived, and it's definitely not the same because of the reasons we just saw. The next question is asking us, what is the purpose of phase milling operation in solid ground curing, which we saw? Was it to ensure a good surface finish? Was it to remove the wax before deposition of the next resin layer? Was it to maintain the Z direction accuracy? Or none of the above? The phase milling in this case was used to remove the excess wax, but the surface finish is ensured from the deposited material and not the support material only. So option A is not correct. It did remove wax before the deposition of the next layer, but not all of it because in this case the wax was acting as the support material. So option B is also incorrect. Indeed, the purpose for the face milling step was to maintain the Z direction accuracy. The next question is asking us, which of the following processes does not require the explicit calculation of support structures? Is it solid ground curing? Is it envision text per factory? Is it robotic SLA, or some combination of them? Now, as we saw, as I just said, in the case of solid ground curing, the wax itself acts as the support material, and this wax is spread over the entire layer without explicitly calculating for regions requiring this support. As we use a mask, which is the negative of the region to be cured, and in all the uncured regions, wax will be deposited. So it does not require the explicit calculation of supports. This is not true for perfect tree because in that case we do require the calculation of support structures. In robotic SLA also, because of the motion of the flexible robotics, the need for calculation of the support structure itself may be eliminated, thereby also eliminating the need for calculating them. And thus, both options A and C are suitable in this case. That was the last question for this week's problem solving session. And that also brings us to the end of the live session for today. So I would like to thank you for tuning in to week 5 of the live sessions for the NPTEL course on fundamentals of additive manufacturing technologies. I am Sourav Goswami from IIT Bombay, and I hope to see you again next week. Thank you very much.